behavior of an amplifier. We model it as a linear time-invariant dynamic system, basically what we do. And you use that differential equations with constant coefficients, linear differential equations with constant coefficients, which means such a differential equation says a number of derivatives, the sum of a number of derivatives of a response equals the sum of number of derivatives of the excitation. Excitation is input signal, response is output signal in plain English. So here, this is the language and this is the math. It's the other language. So here we just say a number of derivatives of y, which is the response. Constant coefficients, these are not functions of time. The derivatives are not squared or to the third order. No. You can have order the third or the second derivative, but that's something else. It's linear. And here we have the excitation, the input signal, and a number of the sum of the number of derivatives of the input signal equals the sum of the number of derivatives of the response. Already telling you something about an essential property of dynamic system is memory. They have memory. Look, if I make this input signal 0, it says that the sum of the number of derivatives of the output signal should be 0. It doesn't say that the output signal should be 0. There can be an output signal even though there is no input signal. That is energy storage in the system, and the system goes to rest. There are losses, and at the end, the system will be at rest because there are no input signals. That's the energy storage. That is what we call dynamic systems. They have memory. And now, how do we solve those things? Well, we know that if we put an exponential function in a derivative, it will be, and we take the derivative, it will again be an exponential function. So exponential functions retain their shape under differentiation and integration. Same with sinusoids and cosines. And that's why you have your sine wave generator on your lab table, because if you want to know something about the deviation from linearity, you can say, well, then a sine wave is in and there is no sine wave out. Then it must be nonlinear, because if it's a linear system, you put a sine wave in it, there will be a sine wave out, and they will have a different amplitude and a different phase, but that's the only thing. That is the property of linear dynamic systems. So Fourier, therefore, writes a signal as a sum of sine waves. Well, exponential, imaginary exponentials. And you could solve your equation with this under certain conditions. Under conditions, well, I don't want to go into the mathematical definition, but practically your system should be stable. You must have bounded responses to bounded excitation, and an unstable system doesn't have that. And of course, it should still be linear. Laplace writes it as a sum of complex exponentials. And that has, it is usually that you can apply this rather than this one, because you don't have this condition for bounded signals here. So with this Laplace and Fourier transformation, your differential equation transforms into an algebraic equation. I hope you know this from your lectures on math. And it looks like this. So here you have then a transfer function in Fourier domain written, and here you have it in the Laplace domain written, and it relates the complex amplitude of the response to that of the excitation. That is what it does. Y g omega and x g omega are the amplitude, the complex amplitudes for at a certain frequency of your response, and excitation respectively.